It's my pleasure to introduce Animashree Anandkumar. Anima's had a really bright start to her career so far. She got her bachelor's from IIT Madras, a PhD from Cornell, and did a postdoc at MIT. And Anima's made many important contributions in areas of spectral methods, graphical model structure learning, and latent variable models. And this work has been recognized in numerous ways, including a number of paper awards, a Microsoft Faculty Fellowship, ARO Young Investigator Award, and an NSF Career Award. And so today, Anima will be speaking on guaranteed learning of latent variable models. Thank you.
Thanks, Emily, and it's a pleasure to be here. So today I'll be talking about how we can provide guaranteed approaches for learning, a wide class of latent variable models. And in particular, I'll focus on two important settings. One is the popular community detection setup, where the task is to learn hidden communities in a network. And we'll do the challenging case where the communities can overlap. So you can have nodes be in multiple communities. And the second setup that I'll deal with is overcomplete representations, which have been very popular recently for feature learning in many applications. So let's look at a set of applications where latent variable models are very applicable. So as I said, the task of understanding how humans form communities, how these different communities of people interact, both in online and offline setting, so how we can do this in an efficient manner. So here the observations are the graphs, right? So you look at a network of social ties, which can represent friendships, say co-authorships, and so on. And what's hidden are these communities of different people. So how can we learn these communities efficiently? You can also think of recommender systems under these probabilistic frameworks. So you can now think of hidden attributes of both users and hidden attributes of products. And how different users rate different products is based on these hidden attributes. Right? So if we can learn these attributes efficiently, then we can do efficient prediction for how to recommend useful new products for users. Right? So the popular framework of topic modeling, where the task is to look at observed words in a document corpus and to summarize the documents efficiently. So you could also think of image or speech analysis in addition to text modeling, where the task is to now look at these hidden variables, which you can think of as a summarization of this document corpus. Right? So what's hidden are these topics, and what you observe are these different words in the document here. So you can think of various settings where you want to learn a useful feature representation of your input data, so you can do many tasks such as classification efficiently downstream. So the intuition is that in this feature space, you have an efficient representation. For instance, it could be a sparse representation. It could have some low-dimensional structures, and so on. So the question is, how can we do these efficient transformations of data into good feature spaces? Right? And we can again view this as a latent variable model if you think of like a latent space under which we represent our observed data. So this is another setup where latent variable models can be useful. So I've been also interested in employing some of the techniques I've developed in computational biology. So here there's a rich set of problems where latent variable models can be very effective. One setup where we in fact incorporated is for modeling different groups of genes. So what we observe are expression levels of different genes, and you can think of what is hidden are, say, different regulators. So I'd like to see how different groups of genes regulate some, say, functional or different properties. So how we can find these different groups of genes and how we can kind of explain the regulatory mechanism is another framework where latent variable models can be effective. So in all these different applications that I described, there is a statistical framework, right? So what we are positing is that the observed data is generated from some set of hidden variables. And the task is how to learn these model in an unsupervised manner. So here we don't have the labels for the hidden variables, and can we still do learning efficiently? So this is the challenging setup. So the very first aspect is to first think about what is a set of reasonable statistical constraints to enable efficient, to come up with a nice model, right? So this one is not very informative. It's just saying there's some set of hidden variables that lead to these observed data. Suppose we have further constraints on the model. So you can think of like the framework of graphical modeling, where I have a graph that represents various conditional independence relationships. For instance, you can have like a multi-view model where instead of like, this observed variables can be now divided into different groups, and these different groups are conditionally independent given the hidden variable. So this is like now imposing further constraints than the basic model. Right? You could even impose further, models which have hierarchies of different hidden variables. So now we can think of a statistical framework involving these graphical models to come up with constraints between hidden and observed variables, which are reasonable in these applications, and we'll see will lead to like tractable solutions. Right, so the very first question that comes up is identifiability. Once I have a statistical model and I have this, observed variables, the question is, when can I learn this model, right? Given, of course, infinite data and computation. So the question of identifiability only worries about, like, are these model parameters really identifiable if, I had infinite amounts of data and computation. But of course, I don't have the hidden variables, right? Only in the observed part. So that is the very first question. In general, unless we assume some constraints, the latent variable models may be non-identifiable. So the next question is, okay, identifiability is a good property to have because this gives us, hope in recovering the model efficiently. But the question is, can we really do it with finite amounts of data and with finite amounts of computation? So that's where the computational framework comes in on how we can provide algorithms with consistency guarantees and with low sample and computational requirements. So typically we are, in all these applications, the problems are high dimensional. So if we think of the community detection, we want to do this on graphs with millions of nodes, if not more. Right? So these are all huge, large-scale problems. So it's pertinent that we ensure efficient methods. So if we look at like standard methods that are used in practice, such as say expectation maximization or variational-based techniques, they don't have any consistency guarantees. So they are not guaranteed to go to the global optimal solution. They just go to a local optima, which can be much worse than the true solution. Right? And of course, the bad news is if I wanted the optimal solution, which is the maximum likelihood estimate, that is a NP-hard problem. So I cannot solve this algorithmically in an efficient manner. So given all this bad news for the general setup, how can we come up with a efficient method for learning a class of latent variable models? Right? So that's where I'll look at some very simple approaches and use the structure of the problem to come up with guarantees. So the intuition is, if you think about, if you pose the learning problem for a huge class of latent variable models, you can think of it as a non-convex optimization problem. So in general, I can think of some very simple update rules. These could be like alternating minimization, some iterative updates that lead to a local optima. But in general, this doesn't have global consistency guarantees. So what we'll show, like in this talk, what I'll present are strategies to, in fact, even guarantee global optimalities. So we will get to the correct model in spite of this non-convex aspect. And that's what I would say is the takeaway of this talk, that these problems in general look hard, but there are some nice, interesting structure in the problem that makes it tractable. And in fact, we can solve them with very efficient sample and computational complexities. And we'll also see in practice that they're scalable to huge data sets and are very competitive compared to these kind of standard heuristics such as EM. So that's kind of I would say, the whole outline of the talk. And I'll focus on two specific latent variable models for concreteness. One will be this community detection application. The other will be learning these set of overcomplete representations. So the very first question is, what is a reasonable statistical model for explaining how humans form different communities and how people in different communities interact with one another? So very popular framework is to think about what are the interests of different users, right? For instance, it could be dancing, computers, tennis, and so on. So how people interact with one another is based on their interests. For instance, these two people may meet in the context of dance, and then they decide to form a tie. And so users could interact under different contexts and then form ties based on this. Right, so with this intuition, there is a popular framework for modeling communities, which is the mixed membership stochastic block model of Iraldi et al. So here the intuition is for every node in the network, there are some set of hidden community memberships. So every node has communities, has membership in some different communities, and they're also weighted. So you can think of like some fractional kind of membership into different communities. For instance, the person may be like interested, say, 40% time in dance, like 20% time in computers, and so on. So you have like a weighted membership into various communities. And then the assumption is when people form edges, right, these edges are conditionally independent given the community memberships. So this seems like an intuitive assumption that, like the edge formation is explained by the membership of the nodes into these communities, right? And when it comes to the probability of an edge between any two nodes, we think of it as a weighted average of all their community memberships. For instance, think of the setting if these two nodes were purely interested only in hiking, they'd have certain probability of forming a tie. But because there was only some amount of weight there, into hiking, it's weighted by those. So for every pair of communities for these two nodes, there's a certain probability of connection, and then I weight by the actual membership into those community, and I get this average probability of connection. And that'll be the overall probability of the edge in this model. Right, so far what I've described is the idea that once I have these fixed set of communities for every person, the edges are formed in a very intuitive manner. Right, they're conditionally independent given the community memberships, and the probability of a single edge is kind of a weighted average of the memberships in the two nodes forming that edge. So the one other thing that needs to be described is how are actually these nodes forming different communities, right? So what are the memberships of these nodes into various communities? So here an assumption is made that there is a prior. So these community memberships are drawn from a Dirichlet distribution. So the Dirichlet distribution is on the simplex. That's because we are assuming like fractional membership. So all the memberships are normalized to 1. And the intuition is that in certain regimes, you can have sparse memberships under this Dirichlet distribution. For instance, if you take this parameter, which is called the concentration parameter of the Dirichlet distribution, and look at the limit of it going to 0, it's a degenerate distribution. So this distribution is only concentrated on the vertices of the simplex. Right? So the only realizations possible are the basis vectors in this setting. So that means a node can be only in a single community. So this, in fact, is the classical model. It's the stochastic block model for those who are aware of this line of work. So the nice thing is, even though we can incorporate a node being in multiple communities, in the special case, we can recover the popular stochastic block model. And so the idea is as we increase the concentration parameter, there is more probability mass towards the center of the simplex. And as I increase the concentration parameter in the limit, it kind of goes to a single point at the center of the simplex. So this is the idea that depending on this concentration parameter, I can get different levels of community memberships. Right? So like kind of roughly the sparsity level of community membership is dependent on this parameter. So this is the nice thing. I can model like now communities with different levels of overlap based on this concentration parameter. So that's the nice thing about this set of mixed membership models. It includes the stochastic block model as a special case, and it can now have a flexible way to incorporate a wide range of overlaps between the communities. So let's look at just some simple visualizations of how the graph looks once I have the communities under this model. So if I had the stochastic block model where there are just nodes purely in one of these three communities, and here I'm assuming there's higher probability of connection within the same community compared to outside, you can see like a nice block structure, right? So you can visually see, oh, okay, this should be a community, this should be a community, and so on. But with mixed memberships, the picture is more complicated. So even visually, you can see that now these colors represent like now nodes being like in multiple communities, and the it's not so clear on how I can learn what the communities are, right? So the graph looks more complicated. And of course, as I increase the extent of overlap between the communities, that was this concentration parameter of the Dirichlet distribution, I have I'm even less certain of what the communities are. So this picture should intuitively tell you that as I have more and more overlap between the communities, it becomes a harder problem to learn the underlying communities. So that's the question we'd like to ask. Can we have a unified approach for being able to learn a wide range of models with different levels of overlap? And what are the requirements as I have increasing levels of overlap? Right, so the intuition is that the sample size is related to the size of the network. Right, so as I get a larger and larger graph compared to the number of communities, I have more measurements. So it's intuitive that if I have a model with more community overlaps, I would need a larger graph for learning. The question is, how should these sample requirements scale? Do they scale gracefully? That's what we'd like to answer. Right, but the nice unifying assumption that will exploit is this conditional independence relationships. And that's, I would say, is kind of a running theme in many of my works, that how the statistical assumptions also lead to computational tractability. So here the assumption is that the edges are all conditionally independent once I give you the community memberships. And we'll see how to exploit this in a good.
The community memberships is a probability vector.
Yes.
So not just a single membership. Okay.
Right, and that's the point, and it's drawn from a Dirichlet distribution. So depending on the concentration parameter of the Dirichlet distribution, we can have different levels of sparsity in that approximate sparsity in that vector. Okay, so this is the model now. Let's see how to learn this efficiently. So in terms of related work, indeed, like community detection is a very broad area with interest in many different fields. But when it comes to guaranteed learning, the works are much more limited. So the classical stochastic block model, I would mainly classify them into two lines of works. One is based on using spectral clustering techniques. The other more recent one is to do convex optimization. And in these settings, there are good guarantees. There are questions of how large should the graph be compared to the number of communities, how sparse or dense the graph should be to enable recovery. But when it comes to learning community models where communities can overlap, the work is much more limited. And the previous works are not probabilistic approaches. They are based on combinatorial approaches. They're very different from this current setup. So I'd like to emphasize that this work that I'll present is the first one to guarantee recovery of overlapping models under this probabilistic framework. And this is a unified framework that can handle a wide range of community overlaps. And as I said when I first started, the first question was, what is the identifiability criteria? Right? So can we first show that the model is identifiable? So what we show is, in fact, this model is identifiable if I had very simple kind of functions of the data. And that function is the subgraph counts of simple objects, which are 3 stars, which I'll come to in a minute. So this is a moment-based approach. So it looks at the moments of this graph. We have a random graph here because we are assuming a probabilistic model for graph generation. And given moments of this graph, in fact, the specific 3-star subgraph count, we get we can identify the communities and we can identify the model. So this is the nice thing. So the next thing is, given samples, how does this method perform? So what we show is very efficient sample and computational complexities. In fact, the sample complexities turn out to be close to the lower bounds in the special case of the stochastic block model. So up to polylog factors, we achieve lower bounds, which have been very well studied in the context of stochastic block models. This is like the kind of the clique detection problem, in CS theory, and the other one is like, how, what is the limits of sparsity that the graph can be. So the intuition is if the graph is extremely sparse, it's harder to learn the communities, and we can go up to the limits of that sparsity. And the other nice thing that I was alluding to before is how should the network size scale with respect to the extent of overlap between the communities. And we again have a very graceful requirement, so it's only just a slow order polynomial. So the idea is even as you have these models with more and more overlaps between the communities, we can still learn them efficiently. So that's like the broad set of contributions. So now let's see what is the approach we take, right? So how do we come up with these guarantees? So as I said, the idea is to utilize the moments from this random graph distribution. So for graph, if you want to think of moments, we can think of different subgraph counts, right? But we'll focus on a very specific one, which is a star with 3 leaves. And we'll in fact show that this is sufficient to guarantee identifiability, and then also learning with samples. So we'll construct this 3-star object in a specific manner. So we'll divide the graph into randomly into 4 parts, roughly equal parts. And we'll, for every set of triplets in these sets here, A, B, and C, we'll count the number of common neighbors in this set X, right? So that's exactly this object here, M3. So for every triplet here, I'm asking how many common neighbors do these nodes have in this set X here, right? If G is the adjacency matrix, it's exactly this, right? You want all these 3 edges to be on, right? And then you're counting over all the set X, how many such edges are on. And I'm normalizing it by the size of the set. Right, so this is essentially like kind of counting. Think of it as a 3rd order moment for these triplet of nodes, right? So this is a 3rd order tensor. So for every triplet, I'm asking how many common neighbors there are there. But I'm partitioning these nodes into different sets to avoid some dependency issues. We'll see in a minute why exactly this is helpful. But this is a very intuitive object. It's like kind of counting common neighbors for groups of nodes. Right, and if I write it as a tensor product, right, this entire the 3rd order tensor, it's a tensor product of the neighborhood vectors of this node X to each of these sets A, B, and C. So these 2 are equivalent, right? So both are, this is just the tensor notation here. So this is my, 3-star, count object. So the very first question for a moment-based method is if I had exact moments, right? What kind of guarantees can I give? And then we can argue that with samples, we'll get close to the exact moments, and we have perturbation guarantees, so we can turn them into sample complexity bounds. So the very first question is, if I look at the expectation of this moment conditioned on the community memberships, what is the algebra that it's inducing? So for this, again, precisely the conditional independence relationships help. So this is where kind of we'll be exploiting statistical properties to get good computational algorithms as well. So here the intuition is we'll use the fact that these edges are conditionally independent once I condition on the community memberships. Right? So if I look at the set of edges here, so from this node X to this set A to B and C, the only common factor there is this community membership vector of this node X. Right? So conditioned on this community membership, all these edges are conditionally independent. So you can think of this as kind of 3 independent views conditioned on this latent variable, which is the vector of community memberships for node X. Yeah.
I'm a little confused. Why doesn't it also depend on the community memberships of A, B, and C?
No, indeed, but they are disjoint sets. The only thing that's kind of common to them is this. So in this set, they are not. There's nothing relating them. So yeah, there are those parameters here, and that in fact is given by this linear map. So there is a matrix here that kind of takes this community membership vector to this set of edges in expectation. And so that would determine this matrix. But what is tying these 3 different random variables is only this community membership of this node at node X. And so that's the nice thing. So if I think of each of these view here, it's in expectation, it's just a linear model. right? So, and now for like these three views, exploiting the conditional independence relationships, we can in fact show that it has a specific tensor form. And from now on, it'll be this kind of tensor algebra that will enable us to do efficient detection. Okay, so the conditional independence relationships helped us form this nice, tensor in expectation. So let's now see what are the properties of this tensor. So intuitively, like if I think of this tensor, it's a sum of k terms, where k is the number of communities, and each term is a rank 1 tensor. So the definition of a rank 1 tensor is just very similar to the rank 1 matrix, right? So here, if I have uww to be a rank 1 tensor, that means if I take like a particular entry in that tensor, which is the ijkth entry, I'm only going to look at the particular indices of those vectors, right? It's like ui times vj times wk. So I have this property that my tensor in expectation is a sum of k rank 1 terms. So this is a big constraint, right? What I have is a tensor of size about n cube, where n is the size of the network. So there are that many kind of observations, but the constraint of this being rank k means there are only very few free parameters. So I should be able to do this decomposition and then utilize that for learning. So the main intuition is that once I can do the decomposition of this tensor, I can learn the communities through some very simple linear algebra operations and thresholding. So I won't get into those details, but the main message is that the bulk of the algorithmic work is in ensuring that we can do this tensor decomposition efficiently. And of course, we have to do it with samples, so we have to worry about how perturbation affects the decomposition of these tensors. So that's the main work here from now on. Okay? So, and of course, the sample complexity will have to ultimately vary that how large should n be compared to k, right? So that's given by the concentration bounds. Yeah, so we'll proceed finding this tensor decomposition in 2 steps. So the main intuition is if I try to decompose the tensor as it is, this may be hard to do. So we'll first convert it into a tensor that is more tractable and also in a lower dimension, and then we'll do decomposition of this tensor. And we know this transformation, so we can then go back to this original tensor and find these components. So the intuition is because this is a rank k tensor, I only need to do decomposition of a k cube tensor rather than an n cube tensor. And this is a very popular philosophy, right? Even for low rank matrix approximation, there are all these dimensionality reduction techniques which are much more efficient to carry out rather than doing exact SVD. So this is a similar philosophy, but it's a bit more involved. So we'll do dimensionality reduction based on data. For instance, we'll use pairwise moments, and we'll compute this transformation based on this information. And what this allows us to do is not just reduce the dimension, but convert it into a tensor which is much more tractable. Yeah.
You basically have a data tensor
Yeah.
that you construct, and so this has a bunch of counts in it.
Right.
And is the rank of that going to be higher than?
So in expectation, it's only rank k, but with samples it'll be noisy, right? So it's like.
Higher or lower?
I mean, it would be to higher, right? So like, if you think of like a generic tensor, I mean, k is usually much less than n. So this one is like saying under expectation, you have a low rank tensor. Now we have an approximately low rank tensor.
But if it's very sparse, it might.
And it will also be sparse, so that'll be determined by like the edge density. And so that is also, a problem we'd like to address, like what is the levels of sparsity under which we can guarantee recovery. So I'll come to that as well.
And when you say tensor decomposition, so you have this, what will generally be a tensor of higher rank than k. Are you talking about least squares approximation?
So that's what I'm describing. What is the strategy to do it? So this is not a least squares problem because this is not non-linear, right? There are 3 modes of the tensor. So how to convert it into a tractable problem? So what I'm describing is the first step where we'll convert the tensor to a lower dimensional tensor, but is also an orthogonal tensor. So this is a much more tractable form than this one. And we'll decompose this tensor and then go back to the ambient dimensional space. So that's the first aspect, that this tensor here, under expectation, this would have been a symmetric orthogonal tensor. So what does such a property give us? So if I had a tensor now where the different components are orthonormal to one another, and if I reduce the tensor along two of the modes. So this is like kind of intuitively, I'm kind of taking inner products along these two modes of the tensor. So that is exactly this one. Because of the orthogonal constraint, the only component that survives is the one that I hit it with. Right? So what is this? This is the stationary point of this iteration, which is the eigenvalue iteration. So this is very similar to the matrix eigenvalue problem. The only difference is this is a nonlinear problem. Right? And what we are saying is, if I had an orthogonal tensor, the components of this tensor are in fact the eigenvectors. So once I have this property, now I have a mechanism to do decomposition efficiently. So you can do a very similar power update as in the matrix setting. So I'm going to initialize with a random vector. I'm going to iterate along two of the modes and keep just normalizing and keep proceeding. Right? And I can do it for a certain number of runs. I can then deflate that out to do the next one and so on. So very similar in lines to the matrix setting. So this is the basic setting. Right? I mean, there's a number of algorithmic improvements we would have to do because we have samples, so there's perturbation of this tensor, and we have to carefully control the perturbation. I won't go into those details, but I'll be happy to talk that offline. So, but the basic method is that we've converted our original tensor to a lower dimensional tensor, and because of the orthogonality, we can convert it to an eigen decomposition problem. But this is a tensor eigen decomposition problem. We can run on the lines of power updates and recover the solution. So that's the overall basic approach. So now we'll see how this method performs under samples, right? So what are the guarantees for this method? And that's the next part. So there are two things. One is the sample complexity. So how large should the network be compared to the number of communities? The other is the edge density. So how sparse can the graphs be compared to the scaling of the nodes? Right, so here k is the number of communities, n is the number of nodes, and you can see that n scales as k squared, which also is the lower bound because in this special case that I've described here, all the communities are of size square root n in the at the lower bound case, right? And which is also the limit for detection in a computationally efficient manner. It's the lower bound. So that is the nice thing. And then the other part is so that would have been the setting with the stochastic block model. So if you recall, when this concentration parameter is 0, we recover the stochastic block model results, the best results for the stochastic block model. But even as the community overlap increases, I have only graceful requirement for my number of samples. It's only cubic in that parameter. So that's the nice thing about sample complexity. It's low order polynomial. And the other is this edge density. So here I've just assumed a simple model where P is the probability within the same community if two nodes are purely in that community, and Q is the probability if they are purely in two different communities. Right? And intuitively, P minus Q is like the separation. You'd like to have more edges within a community compared to outside. And this normalization is kind of by the standard deviation of these edges. And intuitively, this is the scaling. So what this is saying is we can go up to this being polylog over n, which means we can handle graphs with just polylog degrees, which are extremely sparse graphs. So again, there are lower bounds known, up to polylog factors. We are meeting the lower bounds for sparse graphs. Right? So no other method can do better. There is not enough statistical information if I have graphs with lower edge density. So that's the results. We can have tight sample complexity as well as edge density requirements for our method to work. Right? So this appeared in Colt this year. And so what is the flavor of results? So I said these are the requirements. So now we'll have to say what recovery means. Right? If in the classical stochastic block model, each node is only in one community, so then it's just whether you recover it correctly or not. But because now I have a weighted membership in multiple communities, a natural thing to ask is kind of a weighted, is a norm guarantee. right? So for each community, I is the community here, I'm looking at the estimates of the community memberships of all the nodes. And we have an L1 recovery error for this setting. And we can also convert this to support recovery guarantees similar to the stochastic block model setting. So what this result is saying is we can recover all the significant memberships of each node in the network, as well as rule out memberships into communities if the weights in those communities are very small for the nodes. So there's just some middle region where we may not get the right answer, but if the weights of the communities are large enough, I can guarantee correct estimate by the algorithm, as well as if the weights are very low, I can recover correct estimation. Yeah.
Are these probabilistic? Because
Yeah, with high probability.
Okay.
Yeah,
So
so here there's.
So for a given alpha, that controls the
Right.
the
Absolutely.
dispersion of
Absolutely.
the probability vectors. Okay.
Absolutely. Yeah, so these are high probability results. Yeah, so, and these are in fact 0 recovery result for supports. So meaning for every node in the network with high probability, we can recover this, we can have this guarantee. And so these achieve the best results for the stochastic block model, but now we are able to extend it to this whole new wide class of models with overlapping communities. Okay?
Yuri Leskovic actually has been arguing against stochastic block models because he says the probability of an edge should increase with the number of
Right. So that's a
categories
good
you're
point.
in rather than decrease.
Right. So that's a good point.
So-
So the main constraint that comes from this model is in fact due to normalization. So you can think of like kind of other Poisson models or other models without this Dirichlet assumption, where we can still apply some of the techniques with some modifications. But that, we can take that more offline, but it's possible to remove that. In this work we haven't, but I agree with that. But the thing is, it's not so inherent about the mixed membership philosophy, but more to do with the fact that we are normalizing the memberships. So in some sense, we are not, if the two nodes get into multiple communities, they have like kind of smaller weights in those. Right? So you cannot simultaneously have large weights in multiple ones compared to a single one.
While you expect it to have larger weights, or at least the probability of an edge should increase.
Exactly, and that's coming because of this because of
Right.
normalization.
So if I think about alpha 0 in your case, then, or think about how to analyze that setting, do you have any sense of how it will extend or how?
Yeah, so there are different ways to extend. So one is like, assuming that like a Poisson model, not like Bernoulli edges, so I have like kind of think of as a higher edge weight as so then I don't need to normalize the community weights. I can have like kind of, like if I'm in multiple communities, I could have like kind of higher weights than before. And what this method relies on is linearity of the model, and the Poisson models are still linear. So we can extend to that setting, depending on like what, so if it's not Dirichlet, we can assume like other priors which are tractable for this tensor decomposition. The other framework would be not to do this linear averaging of the edge probabilities over different communities. It's a linear model. So if we do like a nonlinear model, like say kernelize it, we could then remove that as well. Okay. Yeah, so in summary, this tensor approach was very effective in recovering the communities, and this is kind of part of a broader framework of learning latent variable models. So in another work, we showed that a variety of different latent variable models can have these moments that have a low-rank tensor structure. If it's not directly the raw moments, you can do some simple transformations to lead to a low-rank tensor problem. So and once we apply these tensor decomposition techniques, we can get very efficient guarantees for learning. So these include Gaussian mixtures, hidden Markov models, and latent tree models, the popular latent Dirichlet allocation, and so on. So in all these models, like kind of, there's all these conditional independence relationships or the structure of the problem that enables us to establish the tensor algebra for this class of models. And more recently, just like very recent work is to look at alternative techniques for tensor decomposition, and we've now been extended to scenarios where we may not have orthogonal tensors, but like incoherent tensors. So there's like different things we can do in this tensor land, and this is just one of them. So, so far we looked at all these very strong theoretical guarantees. These are, close to the lower bounds up to polylog factors. These can handle a wide range of different community overlaps. But how can we, argue in practice what is the performance of this method, right? And this is where, there's a lot of simple, implementation details we can look into to make it scalable to huge data sets. So the very first thing is, for this dimensionality reduction, we need to do singular value decomposition, and this is where we can employ these low-rank matrix approximation techniques. So like random projection kind of techniques make it extremely fast for running in practice. And the crucial aspect, I think, where we get a huge gain is to not form the tensor explicitly. So the way I presented it, I said, oh, look, there is this n-cube tensor, right, this 3-star. But if you were to form it and store it, this is huge. I mean, if n is 1,000,000, n-cube is just meaningless to store. So we'll never be explicitly forming the tensor. We'll only be implicitly manipulating them to multilinear operations. And in fact, we'll even do that in an online fashion. So this step becomes blazingly fast because of these fixes. And the nice thing about these methods compared to the other ones is you don't have to kind of really worry about parallelization. They're inherently parallelizable because they involve matrix products and tensor iterations. So by just design, they're already parallelized, and we even did GPU deployment of these methods. And real-world networks are sparse, so if we undertake sparse manipulations, we can get a very good performance. And so in the end, it turns out that you can show with these techniques the time complexity if you run in parallel using SK cores, where S is the degree and K is the number of communities. So both are reasonably small. It's only linear in the number of nodes. So that's the nice thing computationally, we can get to essentially the limits of how well it can scale. Right, so this kind of covers even the aspect of being able to scale to large data sets. So let's now see how it performs on some just representative data sets where the ground truth is available. So we have ground truth of what the communities are. And then we use a notion of simple p-value based testing to say what the error is. So the idea is, we can go up to 1,000,000 nodes in just a single workstation, and it took about just 1.5 hours. And the stochastic variational method by Dave Bly's group, it didn't even go up to that scale. So even in I think it only went up to 100,000 nodes. It took about a week to run. And on a smaller data set, you can see there's huge difference in running time compared to our method. And also, our method can run without any homophilic assumptions. So, I showed you only models where there's higher edge connectivity within a community versus outside. But for our methods to guarantee results, we don't need that assumption. And in this ELP data set, it's a bipartite setting, right? There are edges outside the group compared to inside. And we have different set of nodes, users, and businesses. And it runs there as well. So let me show just some qualitative results to see what we can say from this. Right? So the intuition is if I want to look at what are the communities that are recovered with high accuracy, for ELP you would expect restaurant, right? Or like this Latin American restaurant category would have high recovery rates. What's interesting is even smaller categories like these hobby shops are also recovered efficiently. So the intuition is you could think a set of dedicated users who would go and review such businesses without overlapping with other ones. And the fact that we use a mixed membership model where a node can belong to multiple communities means that we can recover multiple attributes for every node. So you can see a node can be a restaurant, a bar, its location, and so many different features. So that's the fact, in summary, we can, for this community detection, we have pretty much, reached the limits of, sample complexity. We have very efficient computational complexity which can be parallelized. And this is also applicable for a wide range of data sets.
how you measure the accuracy of community detection?
Yeah, so I didn't go into the details, but the idea is there's some ground truth communities, and I have my recovered set of communities. First, I'm going to match them based on p-value testing, like which ground truth communities are close to this one. So once I do the matching, I look at the error in the, like membership in my estimated communities. It's like a L1 norm, for instance. So in these, we had the ground truth. Like the DBLP, it was the journals and conferences. ELP, like it was business categories. In Facebook, in the small data set, it was given. Okay, the details are in the paper. So now I'd like to switch gears and go to the point of overcomplete representation. So this framework of doing tensor decomposition technique relied on being able to reduce it to an orthogonal tensor. And for that, necessarily, you would have to have this latent dimensionality being less than the observed dimensionality. But what if it is not the case? What if I'd like to learn models where I could have a latent space with higher dimensionality than the observed ones, which is the case with overcomplete representations? So can I still provide guaranteed learning? What are the bag of techniques? What are the modeling assumptions that make it work? So I'll be looking at it under two frameworks. One is the popular topic modeling framework that I'm sure many of you are aware of. But here we'll assume overcomplete models. So here the number of topics can be even larger than the word vocabulary, which is possible for image or speech signals which are complex. And the other is the popular dictionary learning or the sparse coding framework. Okay, so these overcomplete representations can be very relevant for feature learning in a range of problems. So when it comes to these topic models, I'm sure you're all aware of this bag of words model. So here the idea is that each document has a set of topics, right? So for instance, here industry and research for this document, right? And how I draw words is first I draw one of the topics from this mixture of topics, and then I draw a word according to some distribution. So it's a bag of words model because the order of the words does not matter. This is an exchangeable model. And I have all these set of conditional independence relationships, which says that the words are conditionally independent given this hidden topic mixture, right? Given this variable h. And how different topics lead to different words is determined by this topic word matrix or the conditional probability table. So this is mapping different topics to different words in the vocabulary. So now we are going to look at overcomplete models where the number of topics k can be much larger than the vocabulary size, which is d. So although I use these text analysis setting for illustrative purposes, this is much more relevant for, like, say, image signals, where you can think of similar topic models. Right, so again, we'll think of this moment-based approach similar to what I described before, which is to look at co-occurrence of different sets of words. So if it's pairwise co-occurrence, then it's like for every pair of words, what's the probability of them occurring together in the same documents? And if it's higher order, I'm looking at different, larger sets of words and asking the probability of co-occurrence. So the main difficulty here compared to the previous setting is overcomplete tensors in general are NP hard to even determine whether there exists a decomposition. So these could belong to a much larger, harder class of tensor problems compared to the previous scenario. So in general, if I had this bag of words model, in fact, we can show that it's not an identifiable model. So this seems like a stopping point, right? So how do I go further? So what we'll show is a simple modification of this popular bag of words model, which in fact is even more intuitive for capturing some of the dependencies. So the idea is that now let's make the order of words also matter. So think of like as, for the first two words, I share the same topic from this mixture, and then I'm going to switch to a different topic. So locally, I have persistence of the same topic for some set of words, and then I'm going to switch to a new topic. And this is intuitive because you can think of like locality, the assumptions that locally there's like this document is about the same topic. Then after that, I'm going to switch to a different topic after some step. Okay, so using this framework, what we can in fact show is this topic word matrix under some sparsity assumptions becomes identifiable even if I have polynomially many topics than word vocabulary. And you can also do learning through an L1-based optimization techniques. Okay, so I won't go into the details, but what I've shown is it's possible to do tensors even beyond where the rank is even higher than the input dimensionality. And this is the power of tensors that's not present in matrices. And by imposing some additional constraints like sparsity, we can come up with efficient methods for learning these tensors. The other framework is the popular dictionary learning framework, where I assume that each sample is a sparse combination of dictionary elements. Again, this problem is challenging if I have an overcomplete dictionary. So the intuition is that if I know the dictionary, this is just the compressed learning problem, compressed sensing problem, which is well known. But now I don't know either the dictionary or I don't know the coefficients, right? It's a biconvex problem. So how do I do this efficiently? In general, of course, if I did alternating minimization between these two parts, this only goes to a local optimum. So what we show is under a natural incoherence assumption that these different dictionary elements are incoherent, that in fact we can get exact recovery. So these are like the first results for guaranteed exact recovery of both the dictionary matrix as well as the coefficients. And what we propose is kind of a simple initialization strategy for alternating minimization that can be done efficiently. So in the end, although this looks like a hard problem, we get the global recovery results. Okay, the details are in this paper. But I'd like to conclude by saying that I've been interested in a range of different latent variable models and incorporating statistical constraints in terms of conditional independence relationships for guaranteeing consistency, low sample and computational complexity for these learning methods. And compared to like heuristics such as EM or variational Bayes, we have guaranteed recovery of the true model. And I would put them broadly into two approaches. Like one is the tensor decomposition approach that I talked about in detail. This works very well for undercomplete models where the latent dimensionality is bounded by the input dimensionality. The other more recent framework is this overcomplete models where I can have a much larger latent space, but there are sparsity constraints that make the model identifiable as well as learnable efficiently. And there have been a number of projects that I've been interested both in this line and also kind of well beyond in terms of online learning, in terms of large-scale deployment, in terms of applying it to computational biology and so on. So I'd like to kind of view this latent variable modeling problem as kind of being a very interdisciplinary problem. There's like ingredients from statistics, from algorithms, also social sciences if you think about community models, and optimization. So there's a wide range of different tools and techniques that become relevant here, which makes it very interesting. Thank you.
Does anybody have any questions? Yeah, Pedro.
So one of the structures that you mentioned in the beginning was when the latent variables have hierarchical structure with many levels. Does any of this extend to that case, or what?
Yeah, absolutely. So we have a paper that we've just recently, it's almost ready to upload, which is to learn both the structure, like you don't know the hierarchy, and you don't know the parameters. So and you can do like both of them together. Like this, like kind of essentially you need to do tensor decomposition on different subsets of variables. But if you don't know the hierarchy, then you don't know what those subsets are. So you can do them both hand in hand, and you can parallelize them to a high degree. So we give results on correct recovery of both the structure and parameters by using these techniques in conjunction with some combinatorial techniques for structure learning.
Sorry, Marina had a question.
So this is the obligatory question. In practice, you don't know K. So do you have to repeat the estimation for every K?
No, actually, you can also learn the model order by these techniques because, like the idea is if it's a rank K matrix, if I do the SVD of the pairwise moments, so I can like look at thresholding of the singular values and use that to determine the number of communities as well.
So the incoherence assumption in the last part that you mentioned, you have made an overcomplete basis. So what's incoherent? The solution?
The dictionary elements.
I see.
So you have an
And
incoherent
how does that relate to the RIP condition?
which leads to RIP conditions, right? So these are incoherence.
Is it stronger incoherence?
Yeah, I mean the incoherence is like a basic condition. The kind of RIP is adding to that. Because RIP say, I mean, so essentially if they're random vectors, yeah, they're essentially the same thing. So if I have, vectors that are randomly drawn, they would satisfy both incoherence and RIP to a certain level.
And yeah, Peter.
So follow up to Marina's question. It almost seems like your results might actually give you some principled way of picking the number of groups. Right. So, for example, it seems like if you can get this recovery, then you just pick a K that's too large and let it sort of find the group memberships and shrink naturally that way.
Right, you can also, and that's what we do in practice, we threshold like kind of the weights upon recovery. So we only have the significant memberships. So in that sense, it's less crucial. It only matters computationally, like you don't want a very large K because you'd have to do all those computations. So that's the only kind of worry.
I guess I had one quick question. Can you speak a little bit to the reliance on having discrete latent variables in the framework? Just for example, like HMMs, would it extend to? I
mean, so this whole framework just assumes linearity, right? So this includes discrete, this includes Gaussian, Poisson. So the whole class of distributions that satisfy linearity is fine.
All your sample complexity results are for that more general class?
So the sample complexity would be a bit trickier because the concentration bounds, if it's discrete, then I can do Frobenius norm. For if it's sub-Gaussian, I can do like kind of spectral norm bound. So that would depend on the setting. Okay. But like the approach and the correctness is true for all of them.
Okay. Are there any more questions? Okay. Otherwise, let's thank Anima.
Thanks.